They should have said the poet. The poet. They should have said the poet. The poet.
Sending Poets.
This is Sending Poets, a podcast about ideas. Our goal is to understand metaphorical truths within the beauty we find in the human experience. My name is John. With me is Bob and Tucker. What's up, fellas?
Morning,
Hey,
gentlemen.
Good morning.
And we are continuing three-body problem combos. We're going to keep going with the solution side of things. This time we're going to talk about gravity, specifically Newton's gravity. But before that, we got some feedback on the previous episode in this series. Just a request to recap Bob's new interpretation of the 10 dimensions. So let's start there. Bob, if you want to just 5 minutes or so and kind of re-explain the 10 dimension thing.
Absolutely, and I appreciate the question and the request. So, in essence, what we're talking about is a definition. Essentially, what is a dimension? So, the solution to the requirement, and this is an arbitrary requirement at this point, but the theoretical requirement through string theory of requiring 10 dimensions to make the mathematics work. And so, in the past, we think of two possibilities. One is tiny rolled up dimensions, and the other one is very large, higher dimensions. And so my hypothesis here is that what if we have the concept of definition wrong? And so what we take as a dimension right now is length, height, and width, and time. So those are the four standard dimensions that we utilize. And then we theorize there are smaller dimensions or higher dimensions, etc., to try to get to 10. But what if our definitions are wrong? What if height, length, and width are not dimensions per se, but they're directions? And the dimensions come through the combination of these directions. And so the thought experiment is to break up the universe's dimensionality into quadrants. We have four quadrants that are along the positive length, and we have four quadrants that are along the negative length direction. And so just imagine four little blocks. And along the four blocks, there's a depth. So the back end of the block, if you're looking at it from the front side, is, let's say, the 0 point. And then along the length of the block towards the point of view of the observer, that is positive length. And then if you had another four blocks on the other side, that would be along negative length, but let's just stick with positive length. So from the back end of the four blocks, the 0 point to you, everything is a function of positive length. But then the upper right-hand corner, arbitrarily, would be a dimension comprised of positive length, positive width, and positive height. And then going counterclockwise, the block that's in the upper left-hand quadrant would be a dimension comprised of positive length, negative width, positive height. So I'm defining width, positivity as to the right side, negativity to the left, and height, positivity up, and negativity down. So then obviously the lower left-hand quadrant would be positive length, negative width, negative height. And then the lower right-hand quadrant would be positive length, negative height, positive width. So each quadrant is comprised of a function of three directions. And then the inverse is true going the opposite way. We'll go through each one, but the opposite way. So the 4 blocks behind these 4 blocks are a function of negative length. So the same combination of 3 directions occurs going backwards along negative length. And so that gives us 8. So 8
eight dimensions. Yeah.
8 spatial dimensions. Okay, now to get to 10, we include time. So time is included in the current concept of space-time. So space-time purportedly has 4 dimensions: length, width, height, and time. And altogether, you cannot remove any one of these 4 components. We have something not space, not time, but it's called space-time. Mm-hmm. And it equals 4 dimensions. And that's pretty well agreed upon. But what I'm saying is, maybe we have 4 spatial dimensions, and then 1 of time, and then this is along positive length, and then a la antimatter, or if you want to go multi-universe or multiverse, perhaps there's a second, we'll get to this another time, a second universe out there that's a mirror image of ours that is all a function along negative length. So my proposition is everything that we know today, all of standard matter, not antimatter, but standard matter is all a function of positive length. And then the height and the width oscillating. And then time. So time can be conceived of as a twist. So just like you're looking at a clock and you have clockwise and counterclockwise. So just arbitrarily, let's just say along positive length universe, so the universe of matter that we have, time twists along this direction of length clockwise. And that's a dimension. Mm-hmm. But then there's another dimension of time going along negative length, and it twists counterclockwise.
From the perspective of the clockwise, right? I mean, if you actually, right, like this kind of makes sense. Like if I'm looking at the 4 dimensions and I'm seeing, time, positive length coming at me, right? So in front of me, upper right is positive height, width, right?
Yes.
If I were to, go to the other side and look at the negative length, well, it would also be spinning clockwise. It's all the perspective, right? I mean, if I stay in the one spot, then yeah, that negative would be twisting counterclockwise, right?
The clock, you're exactly right. The clockwise, if you can go to the other side of length, back, you're like turning yourself around. It's like a virtual image. It's like the mirror image of the thing. So it is turning one direction, but only when you're on the positive length side of the 0 point. So once you go to the other side of that 0 point, look back the other way, it looks like it's going the other way.
I do have that. Wait, do I have that right?
You do have that right.
Yeah.
So I'm gonna.
It spins the other way from one perspective, based on if it's positive or negative length.
You would subjectively say it's spinning the other way.
Yeah.
Because you're looking at it from the other side. Like imagine you're looking at the mirror versus being inside the mirror looking out.
Mm.
So when you're now, obviously it's a virtual image, so the mirror does not have depth per se. It's an illusion, but it's a powerful one.
Well, I'm gonna say something that ties into this whole idea. So just quick, as Sagan would say, back of the envelope calculations. So they say 85% of the universe is made up of dark matter and dark energy, not us, basically, right?
Yes.
Something that exists that we can't really detect. So that leaves, so what I just did, take 100 divided by 8, because that's how many dimensions we're proposing. You get 12.5, right? 12.5 times 7, which would be the 7 dimensions that are us, is 87.5.
Well, damn. I'd never thought about it like that. That's very, very, very interesting to me. Very clever, very interesting. I would say the spirit is correct in that what I'm proposing is, and I mentioned this last time, but let me reiterate and reinforce your point, Tucker. I'm proposing we're stuck in the upper right-hand quadrant.
Yep.
Stuck being relative. Okay, that means as physical beings made of matter, we're only cognizant of positive length, positive height, positive width. Electromagnetism can bypass this through its oscillation through the other three quadrants. And this is what gives us evidence that there's additional dimensionality that we are not familiar with or we cannot directly experience, but we can indirectly experience and form a circumstantial evidence case of its existence. But that is precisely what I'm talking about, Tucker, is the vast majority of everything is
not us.
correct. Correct.
Wow.
Yeah.
And another quick add-on is people, justify a multiverse concept in order to make the math work, so to speak. And one day we'll dig into like, why does this math work and why do we start with the math and all the rest? But it is a very difficult proposition starting a priori with these non-evidentiary concepts and then working backwards. But it does seem to work, and that's where we'll get to. But the point is, there's so much more there that has influence vis-a-vis dark energy, dark matter, that we just don't have justification for it. And everybody's trying to find what is the dark matter particle? Where is it? Why do we have dark energy? Because that's the preponderance of the totality of energy and matter in our universe appears to be dark energy, driving expansion, increased expansion, etc. So these circumstantial cases are built upon evidence, but it's not direct evidence. It's indisputable by current standard model physicists, exactly what Tucker just said. The vast majority, somewhere north of 85%, I think it is technically like 87%, is unknown right now. Literally unknown. You cannot point to a place where dark energy comes from. Is dark energy in the room with us right now? That one of those memes, right? Nobody can point to it, but there's very specific demonstrable effects that can be seen and not dismissed. And they're not justified by what we do see. So the hypothesis is something that we don't see that is causing two things. And you're right, Tucker. I think I'm not going to propose that the math is perfectly proportional. I love it. It's very symmetrical and beautiful. And I might steal that idea, by the way. But there's something there is my point. Something there that might be as easily explained as just changing the definition of what a dimension is. Because why is it length? Why is length a dimension? Who made that rule? Show me on a piece of paper a proof that requires length as a dimension and not a direction.
Finish what you're saying.
I was just going to say it's arbitrary. I'm not saying it's wrong, but it is an arbitrary designation of we're going to call length and we're going to call width and we're going to call height a dimension. Okay, why?
Yeah. I like it. It was a little bit more than 5 minutes, but yeah, good stuff and new stuff now too. Yeah, thank you, Tucker.
That was awesome. I love that.
I think that was that's kind of the takeaway this time.
Sorry, John. One last thing before we relinquish on this. Imagine I'm trying to get to the clockwise, counterclockwise. Take an actual clock, because I'm walking in a room and I see a clock and it just struck me. Why don't I use a clock? Looking at the face of the clock, it's going from 12 o'clock, let's just say the minute hand, to 1, 2, 3, 4, 5. And we call that clockwise. Mm-hmm. Now imagine there's no back on the clock and you go to the back side of that clock and you're seeing the clock move and it's going from 12 to 1 to 2. But when you're looking at it face on, it starts going to the right-hand side, sweeps down, and then comes up the left-hand side. If you look at that same clock, twisting that same direction, but you go to the back side of the clock, it's still going to go to 1, 2, 3, but now 1, 2, 3 is to your left.
Yeah.
So that's to clarify your point, John, that it is
okay. So So it's like it's rotating the same direction. It's just, yeah, but still perspective where you're looking at it is where you use the label clockwise or counterclockwise or whatever.
Correct. But from the
Right.
0 point, like the actual point of the clock, it's like a physical mechanical thing. But when you're on the positive length side, what you're looking at is what you would call clockwise. Now, if you had a duplicate of yourself on the back side of the same clock, they would see it sweeping, but instead of it sweeping to the right-hand side, going to the bottom and then up the left-hand side, it would be sweeping to the left-hand side, to the bottom, up the right-hand side.
Yeah, counterclockwise. Yeah.
Correct.
Yeah. Awesome. I feel like Rick Moranis in Spaceballs. Like I want to look at the camera and be like, "Everybody got that?" You know what I mean? Like I need a soundbite for that. But yeah. I feel like that was the takeaway too. Like I like, the length, width, it kind of from Flatland, right? Like length, width, height, dimensions. But why? Maybe those are directions instead of dimensions, and then that really helped me kind of visualize that. Last time it worked, and then I tried to tell somebody about it afterwards. It was just like my brain hasn't fully recovered. I can't remember exactly what was said. But
Well, I think
but
repetition is not a bad thing to
sure,
try to
yeah,
cover these in a condensed form. Each time should be more compressed, more condensed, and then better questions like, specific questions. As you gain a little ground, you'll then see another point of, oh, I just don't quite get, and that helps me and that
yeah.
helps everybody. And Tucker, has a great idea to jump on top, which I'm still trying to I'm trying to focus on the conversation right now, but half my brain is kind of thinking about this.
Like, wait a sec, I gotta focus on. Oh man, yeah, yeah,
Well, and
yeah.
I mean, it even trips me out having just done the math real quick that it's like you look at everything we can see, the billions of galaxies going back 12 billion years, 14 billion years, and there's 7 times more than that that's there somewhere.
The
That
effect is there. Yeah, the effect
we
is there.
we don't even
Yeah.
know what it is. We don't even know what it is, but it has to be there.
Yeah,
Something does, and that's the point. Is it's not correct the way it is, and I don't know if what I'm hypothesizing is any more accurate or correct than what is currently out there, generalizing dark energy, dark matter. I'm not going to go deeper into it. We will get there on the final episode of the series where I propose the solution to the 3-body, the real solution. We're just doing the groundwork right now. We're just trying to
Yeah.
cover terms and have an understanding. We will get to a point where I'm going to propose an actual hypothesis of what is happening in real life, not in a movie sense. I know that it is a TV show and a book, and obviously, but I'm not talking about like a story. I'm saying this thing is underpinned by a real physical phenomenon. The 3-body problem is a real thing. It's genius to incorporate it into a work of art.
yeah,
But it is part of this bigger system I have of, explaining what is unknown right now. What kind of hypothesis, supposition could we put out there? And the 3-body problem is a great illustration of my point.
yeah. Beautiful. I can't wait. And yeah, so let's keep going here. So again, this episode we're going to kind of focus on Newton's gravity. Where we had this article Bob found. Just want to quote a few things to kind of preface the rest of the episode. It was from space.com. The question is, why is gravity so weak? So linked to that in the episode notes. But 3 pieces I'm just going to read real quick. We have no idea why gravity has the strength it does. There's nothing that appears in any theory or physics to explain its strength. There is no accepted solution to the unnatural state of the Higgs mass, and hence no accepted solution to the hierarchy problem and the weird weakness of gravity. And then among the potential solutions, some ideas call into question our understanding of the very fabric of space-time. Nice little preface there. So yeah, take it away, Bob, on your thoughts here. And again, Newton's gravity is kind of the overarching thing, right? So
Let me touch on this real quick just to recap the underlying proposition here, which is there are 4 fundamental forces. There's a strong force, nuclear force, the weak nuclear force, electromagnetism, and gravity. And out of those, there's kind of like a matrix of strength and distance. So some of these fundamental forces have unlimited distance, like gravity and electromagnetism. And then they, and strong and weak nuclear forces have very short distance that they act upon. And then there's strengths. So the strong nuclear force is obviously very strong. Electromagnetism is relatively strong. The weak nuclear force is relatively strong. And then gravity is preposterously weak. Like, I can't remember, billions upon billions of times, maybe even more.
Yeah, I think in the article the number was quadrillion. I think it was like something.
Weaker than the strong nuclear force.
Yeah.
And it comes down to why. Okay, so now we're going to start back on Newton, but I just wanted to underpin that with, there is a very outstanding question of these 4 fundamental forces in our universe that we've uncovered, and there's an imbalance in the force, to borrow a phrase, in that gravity is preposterously weak, and there's no explanation for this thing. Okay, so but now let's go to Newton. One of the geniuses of all geniuses, and very, very, very much a testament to being exploratory without great instrumentation. Okay, we're hearkening back to a time before super colliders and space telescopes and all the rest. Because one of the things I think is fair is, hey Bob, who the fuck are you? Okay. I'll be the first to raise my hand and say I'm a nobody. Okay. And I've got nothing. I don't have experiments at my fingertips. I don't have supercomputers and models and shit. But I do have ideas and I have imagination. And once upon a time, that was enough to change the world. And I'm going to also point to that article and say, with all the instrumentation and all the people on Earth who have PhDs, and God bless them, and they don't have an explanation. Not for gravity. So maybe it's left to the imagination again. Maybe this is the source. Figuring out another way to reimagine the universe such that we can have an understanding that can then spur a test or an experiment, which will then push us forward in a human sense. Like we can all have a deeper understanding. By the way, Newton is not the end all be all. Obviously Einstein comes after Newton, and that's the next episode. So I'm not saying Newton is irrevocably correct for all time. He was not. But for our purposes, we're going to start here. It's very illustrative of some of these concepts. And let's start with a very beautiful concept, probably one of the most beautiful concepts. And we'll get into this, I'm sure, as follow-up episodes. This concept of a barycenter. Very strange word. I think it's from the Greek, about heavy center. So it's about a shared center of gravity. We're going to deal with 2 bodies. We'll get to 3 eventually, but we're going to deal with 2 bodies all this time when we're talking. 2 bodies. And the 2 bodies, as they are in a periodic dance around each other, each one attracting the other, each one with its own position and velocity, they form a new unit. So each body, this is called a sphere, has its own center of gravity, point at which you can balance the whole object upon this one point of condensed mass. It's the center of gravity. So each object has a center of gravity, but when they're dancing around each other in a periodic motion, they have a shared center of gravity, this barycenter. And it's not on one side or the other, it's in between each one. And as they dance, they circle this shared center of gravity. It's a very beautiful thought experiment I'd like to do very quickly, which is to imagine train tracks. So imagine train tracks in front of you, stretching east to west. And so there's a north rail and there's a south rail. And let's just say that there's an object, a spherical object with, 100 kilogram mass, doesn't matter, whatever the mass is. And this is the only object in the universe, these two objects. So one is going to be on the north rail and one's on the south rail. And they're coming at each other at the same speed. So one's on the north rail coming from, let's just say arbitrarily, the west, and the southern object is coming from the east. And there's nothing else in the universe. So they're just flying through space, untouched, at a given velocity.
Same velocity, both of them?
Yeah, let's say same.
One's not, okay.
Symmetrical, yeah. Let's make it perfectly symmetrical. This will be thought experiment of symmetry. The only thing that's not equal is they're not facing each other directly. So one is on the north rail and one is on the south rail. So they're not coming head into each other.
Yeah.
One is on the north rail coming from the west. One is on the south rail coming from the east, traveling the same velocity. As they approach each other, they're going to experience this Barycenter effect, where each one doesn't pull on the other, and the other one doesn't pull on the first one. They both pull on each other at the same time, and they're pulling from the Barycenter. So the shared point between the two of them is going to be attractive to both simultaneously.
And if they're both, and you did say like both spheres are, let's just say, equal mass, right?
Correct. Yeah, exactly.
And that the Barycenter is like an invisible point in kind of right in the middle. Yes, is that fair to say? If it's
in
if
this
it's
case,
two, yeah,
we're setting up symmetry, so it would be exactly in the middle.
In the middle.
Everything
Cool.
is yeah, exactly in the middle. Now, if one was larger than the other, more massive, and one had more velocity, the Barycenter would move, and it's not always this way. But as an example, this is perfect line of inquiry. Everything's symmetrical, so the Barycenter would be right in the middle of these two train tracks. So as they pass each other, they're going to accelerate toward each other. And now they're not attached to the rails, by the way. This is a theoretical. I'm just trying to give you a structure. Right. So they're floating out in space. There's nothing in the whole universe. And as they pass each other, they're going to start pulling in towards the Barycenter and accelerate. But they're going to shoot by each other because they're spread far enough apart that they're not going to strike. As they shoot past each other, the Barycenter is going to slow them down, pull them back. Now they're going to start inverting their trajectory such that the north sphere is going to curl around to the south side, and the southern is going to curl around to the north side, and they're going to come back at each other again. And they're going to set up a periodic orbit around this shared space, this Barycenter space. Obviously, it's a function of their mass and their distance and their velocity, but let's just say it's perfectly aligned such that they go past each other a little ways, then they start slowing down and they curl back around to each other, and then they begin this dance, and this dance will be forever. So they were going to oscillate around this Barycenter in an orbital pattern, an elliptical orbital pattern, and they're going to continuously do this for all time. And this is showing that one item, one mass, does not necessarily create a force upon the other one. They both create a force upon each other that's mutual. This mutual force is always attractive, by the way. It's never repulsive. It's always attractive. So you have this mutual force, but it's shared in a singular space that now is the center of gravity for the system of two bodies. So each body has its own center of gravity, its own center of mass. The two together form a third theoretical place. I mean, it's not necessarily a fixed place. It's a theoretical place. It has no mass in and of itself. It's empty space. It's the space between the two rails. There's nothing there. Yet, it is the center of mass and center of gravity, the Barycenter, for the system of two. So very, very powerful to understand the difference between a magnet acting upon another item, you know, a piece of iron or something, and forcing it through electromagnetism to change itself. These two things are acting mutually upon each other. and creating this new location in space, this Barycenter. And this is
real quick. I want to point something out because I think it's important. When you're dealing with two objects, they don't even have to be the same size and the same mass. They could be completely different by, tenfold, and they will still develop that Barycenter. It wouldn't be in the same place necessarily as two identically sized objects, but it would still develop that perfect symmetrical dance.
It's always there. You're right.
It's always there.
And like, so specifically, right, like with the Earth and the Moon, the Barycenter is somewhere within the radius of the Earth, because the Earth is so much bigger than the Moon. But again, it's not you can't like dig through in the Earth and be like, here, I can see the Barycenter. It's this thing right here. It's invisible, right? We don't see it. Well, it's invisible to our eyes.
Let me give a really good example of this. I think this is perfect segue to this, because Tucker brought up something in the pregame conversation about detecting potentially life on other planets. And one of the ways you can potentially detect life on other planets is as the planet passes in front of its star, the spectrum of light coming through the atmosphere is detectable. You could detect the elements that are within the atmosphere itself. And so if they detect, say, free oxygen, be a very good indication that there's life on that planet. But there's another way. So that only works when the planet transits the star. Now imagine the orbit of the planet is such that it doesn't transit in front of the star. It transits polar to us. So it goes, like a clock would. So the clock, if you were going around the edge of the clock, it would never pass through the middle of the clock, so you'd never see the light. But what does happen is the star will wobble. And detecting the wobble of the star gives you evidence that there is an orbiting body. And then you can give it a range of mass and distance from that star.
Yeah.
But these are 100, and also we'll go into this later on, but the gravitational pull of the Earth. Like, we're all stuck on the Earth because the Barycenter is deep inside the Earth. It's effectively at the center of the Earth because we're so tiny. And we talk about the formula for the gravitation of the Earth upon, humans and small bodies on the surface of the Earth. You don't even have to calculate the mass of the human. It's irrelevant.
Yeah.
And the distance is just the radius distance of the Earth itself. So the distance to the center of the Earth. So you're absolutely right. The Barycenter changes, but it's always there, no matter how big, how small one mass is to the other. It is universally there, and it is such a profound concept. To understand that we pull upon the Earth equally and opposite as the Earth pulls upon us. That's effectively what we're talking about. No matter how big, how small, there's mutual attraction at all times. That's what gravity is about. Mutual attraction and a shared center of gravity that might very well be inside the planet itself, or to the point of the moon. It's not equidistant between the Earth and the moon. It's very much on the Earth side.
Yeah.
But the moon does pull us around a little bit. We do wobble.
Yeah, right. I have a vague memory of a Veritasium video where, somebody kind of had this fun idea. What if you could coordinate an entire continent worth of people to like all jump up at this exact same time, something like that? Would you notice an effect somehow? Maybe it wasn't an entire continent, and I don't think the experiment, I think somebody did do an experiment, but maybe it was hundreds of people, maybe thousands of people at most. But it was a really interesting concept. Like you're saying, like the individual mass of a human compared to the Earth is negligible, but what if you could get,
You would move the Barycenter. That's the answer, is you would move the Barycenter a very small fraction.
Yeah, there would be a measurable effect. Very interesting, right?
I think that the concept is that this thing always exists. And by the way, you could add more than two bodies. We just simplified it, but you could add 3, 4, 5, and then it becomes not so simple. It becomes, we'll get into this, the complexity of the 3-body problem itself is that it's chaotic.
Right.
But why? And then we'll get to why, and that'll be my hypothesis. But I think that the take-home message is it's a mutually attractive force.
Yeah.
And I'm talking in the sense, by the way, we're in a Newtonian sense, so I'm talking as a force and not curvature of space-time. Just FYI, we will get there, and that is the truth. But for our purposes right now, take it as a force. Take it as an attractive only force, always shared by all massive bodies, and creating a new systemic center of mass or center of gravity called the Barycenter.
Check.
Okay,
Everybody got that?
fun fact time. So, and I remember seeing a visual of this, but when you were talking about the entire human race, let's say, if we get everybody to jump at once, would it have an effect? Okay, well, the entire human race, if you blended them down and formed a sphere out of it, would be about 1 kilometer in diameter,
Wow.
which is
Yikes.
not very big, right?
It's not very
Yeah.
big.
Not very big. Much smaller than many asteroids. So yeah, that effect is going to be pretty negligible.
Yeah.
It
Wow.
might not be measurable by human standards. There would be a theoretical
Sure.
differential, but you're right. I don't know if instrumentation now would ever be able to be precise enough to have an accurate result. I agree with that. By the way, that's shocking. I did hear something else, by the way. This is another factoid, fun fact kind of a thing, that the biomass of ants in, I think it was Africa, is equivalent to the biomass of all the humans.
Mm-hmm.
And so we are,
Just in Africa.
I believe so. I don't know if
Wow.
that equates to the humans in Africa or all humans, but the point is, we are tiny. We are infinitesimally tiny. And then think about how tiny
An ant
a
is compared to us.
well, I was going to go the other way. I was going to say the planet is. Think about how tiny our planet is, and then think about how tiny and minuscule our star is compared to our galaxy, and then think about how tiny our galaxy is compared to all the galaxies. I mean, it's
Right.
unfathomably mind-bending how tiny is not the right word. I mean, how what do you want to say, guys? Like the number of atoms that make up your body. I think we talked about this a long time ago when we talked about, like, if the universe was a river, each galaxy is like a little swirl, like an eddy. And then the planets. I mean, it's like you're not even a molecule. You're not even an atom. You might be an electron around one atom in the concept of a river universe. And then each galaxy is its own little swirling, bubbly eddy or something. I mean, we're so insignificant is my point. We're so insignificant on an absolute scale. It's preposterous.
And on that same track, I think it's Spaceman, this guy on YouTube and TikTok. I think it's like Spaceman or something, but he does those visualizations where he's like standing there in a spacesuit and he's like,
I remember
I
that,
just put like, a black hole where New York is, just, size comparisons. And I think he had one where, so Bob, you were kind of describing going out into the universe, and he I think he started with that, and then he came back to the human, and then went, deep into the molecular and quantum realm of things, and how humongous we are compared to how tiny quarks and all that quantum stuff is.
That's a great point, by the
and
way.
really, really mind-blowing,
It
comparison stuff.
it brings up a very powerful point that I will rely upon later on, which is fractal nature of the universe. Symmetries and fractals, things that repeat the same structural pattern, bigger, smaller, it becomes, think of like a Mandelbrot set, right? You have infinite zoom capability. Anybody who's interested, Google image Mandelbrot set. And you've seen it, obviously. It's hard to describe, but it's like a little swirly pattern. Each little edge of the swirly pattern has like, almost look like ferns or like plants or something that are growing off the edges. And as you zoom into those, it too, has more ferns or edges or little frills. Are you guys familiar with the Mandelbrot set?
Yeah, I had to look it up again because it's been a while, but yeah.
I actually did a
the
report
Wikipedia.
on Mandelbrot in middle school or high school.
Nice.
So that's a big part of my theory is going to be the fractal nature of things. Okay. And we touched in the first episode about black holes. So a lot of people, it's not just me, but a lot of people can conceive of black holes as being a fractal image of our own universe. So maybe understanding a black hole, there might be a universe inside, or it might be
Right.
a way to understand the bigger universe ourselves. And this goes back to this concept of you're inside a jar, let's say, and you want to read the outside label of the jar. Well, how would you ever do such a thing? You can't get to the outside of the jar you're in, you're stuck. But if you can create a fractal image of that jar that's inside the jar with you, now you can read the outside label.
Mm.
So the fractalness of reality is a strong indication, as are symmetries, that things can be predictive. And I'm not going to go into them now, but a lot of physics has been uncovered. Fundamental physics has been uncovered through understanding a tiny little piece of something and then realizing it's part of a symmetry, and then knowing right where to look for other pieces that would give you evidence that this is, a system. It's not just a singular thing.
Right. The predictability piece there's huge, right?
Correct. But this is where abstract mathematics and a priori thinking can lead us to truth, theoretically. I mean, not saying all times, but let's go back to string theory and what, the 10 dimensions are based off of. It's based off of mathematics. And somebody said, what if we don't have 4 dimensions? What if we have more? And it just so happens when you get to 10, I think 11 is like M theory. There's another theory that has 11 dimensions. But anyway, it's a mathematical structure that is very powerful, but it's arbitrary. Someone just said, why not? Why do we have 4? Why don't I try 5? Why don't I try 6? And he kept on trying. He kept on adding more dimensionality to this theory. When we got to 10, it started to corroborate with forms of reality, but there's no explanation why. So this is why, by the way, people are backing in. Why do we need 10 dimensions? Well, the math says you need 10 dimensions. Why does the math say you need? Nobody knows.
Yeah. Does this? I've been really excited to hear one of your items on the agenda here. Is one of the first things you asked me, Bob, when we met. What did I think about the gravitational constant? And it was kind of like the we were talking about before the show here. I was like, what? What do you mean? That's brand new to me, and we really haven't like dived into it too much. So I hope I'm not jumping ahead here, but like we're getting into this, right?
Yeah. Let me actually put a bridge out here between this concept of, and I wasn't going to do this, but let me do this because I'm not going to die on this hill. This is not my point, but let me do this. I do have a kind of a symmetrical or fractal relationship with the gravitational constant. And we'll go into it in just a second about its place in the formula of Newton's force of gravity. But let's just say there's this constant that exists and it's a measurement. Okay, it's not a formulaically derived constant. It's a measurement. It's just an experimentally derived value. But let's just say that value happens to have a proportionality to another very powerful constant in the universe, the speed of light. And the formula that I have come up with, and please, everybody out there, and John, check my math, excuse me. And we've done this in the past, so I'm sure you've done it, but if you want to do it again, Tucker, please check my math. The value of the gravitational constant is equivalent to 1 divided by 2 times 5 squared times the speed of light. So essentially 1 over 50 times c is equal to, and by equal, do you remember what it was to, John? I can't remember. It was the decimal points, the amount of 99.9999999 equivalency. I want to say it was like 11, 12 significant digits. So if you do the math and take 1 and divide it by 50 times c, there's a reason why I do 2 times 5 squared. I'm not going to get into it now, but it comes of the symmetry and this fractal nature of the universe. If you take 1 divided by 50 times the speed of light, it is so close to the gravitational constant as to be equal to. I mean, that's a bold statement. But I'm going to say two things about why it's equal to. Number one, gravitational constant is extremely difficult to measure. I think we've only really experimentally measured the gravitational constant to about 4 or 5 significant digits. And number two, the speed of light is fixed by definition to the closest meter per second. So once upon a time, all the scientists in the world had to get together and formulate standard units. So this is why we do things in mass in kilograms and distance in meters and time in seconds. But seconds is a definition. Seconds is like the vibration of a cesium atom or something like that. I mean, there's like these variations of how do you set what these things are set to. And the speed of light being a constant, meaning it doesn't change no matter what your inertial frame of reference is, the observer always measures the same speed of light. That speed of light is set to the nearest meter per second. So if anybody out there, and please, hopefully someone's checking my math in real time.
Yeah, I am.
So Google up the gravitational constant and Google up the speed of light in meters per second, and then take the inverse of 50 times c and compare it to the gravitational constant. And if my memory holds, it's accurate up to, I want to say 12 or 11 or 12 significant digits, which is so mind-bendingly close. It's, according to my estimation, it's equal to. Okay.
I'm only getting up to the third digit.
2.075, 2.076.
So,
but you have to do 10 to the negative 11th to do that. So
yeah, so the math I'm getting is 1 over 50 times c is 6.67128 times 10 to the negative 11th. Gravitational constant is 6.674. So it jumps after the third digit, but that's
with scientific notation. So use the scientific notation to move the decimal point back to its original point.
Oh, gotcha. No, that would be right.
And then count how many decimal points that is.
So yeah, that'd be like 13 or 14.
I think that's pretty close. I'm going to call that equal to. I know it's not technically equal to, but I'm going to call that equal to. And I'm not going to go into why I think this is the way it is. And like I said, I'm not dying on this hill. I'm just saying sometimes you can find a beautiful mathematical symmetry or fractal nature that showcases perhaps a truth in reality. And I'm not claiming that this is, I'm just giving it as an example, putting it on the record that there's something very special about the gravitational constant. And perhaps the tie-in to the speed of light, which is a beautiful idea, but I'm not going to go there. We're going to go back to Newton. Thank you for checking on that. Let's go back to Newton. Now we'll factor in this conversation heavily. Thank you, John, for the segue to gravitational constant, because it's all about the gravitational constant. We're going to talk about Newton's formula of the force of gravity. We're going to talk about the formula of the gravitational attraction of Earth. Those are the only two formulas we're going to talk about. But they both use the gravitational constant, and the gravitational constant is key to the thought experiment at the end of this conversation. So let's start with Newton's equation for the force of gravity. And everybody who went through high school in America probably knows this, but it's the gravitational constant times, and this is with two bodies. Let's just make this explicit. We're doing two bodies right now. So massive body 1 and massive body 2. We'll call it M1 and M2. So it's the gravitational constant times M1 times M2 divided by the distance squared. And the distance is not from the edge of each object, it's from the center of mass of each object. So to reiterate, the formula, let's take gravitational constant out first. Mass 1 times mass 2 divided by the distance squared. It's the most beautiful formula of all time, in my opinion. I'm not even kidding you. And we're going to talk about Newton for a second. So Newton, when he envisioned the apple falling to the earth, how did he make this thing work? Well, trying to remember the exact, it's such an interesting turn of phrase. When I researched this a while back, the concept of Newton's, because Newton uses Earth as the first mass, and then say an apple as the second mass. But the mass of the Earth was not known. I think they call it an inspired guess, I believe is the terminology in the history books, an inspired guess. So the Earth's approximate circumference was known. Its shape is obviously a sphere. So you can get the radius. So you know the distance from the center of mass to the edge of the Earth, which we stand upon. So all they needed was the mass of the Earth. So he had to have an inspired guess as to the average density of the Earth. I'm not kidding you. So Newton, back in 1600 something, had an inspired guess to the average density of their planet, used the fact that he understood it's a sphere and it's got a radius of this, because of the circumference and the diameter and pi, you can figure these things out, obviously. And then factoring in the density, you can get to the mass of the Earth. The mass of the Earth. Using the mass of the Earth and the radius squared, so the radius of the Earth itself squared, you can now back in to the gravitational constant. So think about that for a second. So the mass 2 is relatively, it's zero, essentially. It doesn't matter. I mean, it's not zero because you're not multiplying by zero. But essentially, all you need is the mass of the Earth to achieve a formulaic understanding of these parameters. So you know what the radius is, which gives you the distance from the center of mass of the Earth to the center of mass of you standing on the Earth. And let me redefine real quick. I'll go backwards. I'll go back to the force of gravity in a second. But what we're talking about is Earth's force of gravity. Earth's force of gravity upon apples and humans and anything on the surface of the Earth. This is how Newton figured it out. Get the mass of the Earth. We know what the radius of the Earth is. And then test the acceleration of an apple falling. So once you can test the force, you know what the force is by timing it. You've got all the force. So the formula is F. So the force, Fg, force of gravity, equals the mass of the Earth divided by the radius of the Earth squared. But it's not right. It doesn't work. It doesn't work perfectly. What you need is a constant in there, this gravitational constant that then allows you to use all the other terms that we've used, meters and kilograms. So he backs in experimentally to this gravitational constant. And let's go back to the actual formula, because I think this is so beautiful and so illustrative. You have mass 1 times mass 2 divided by the distance from their centers of mass squared. Okay. Now, I'm going to propose something that will go back to our initial conversation about the 4 fundamental forces. Why is force of gravity so ridiculously weak compared to the other 3 fundamental forces? And the short answer is the gravitational constant. Tucker, what was the gravitational constant again? Please read that out.
6.674 times 10 to the negative 11th.
10 to the negative 11th. 10 to the negative 11th is such a small number, it boggles the mind. And another day we'll talk about electromagnetic force and Coulomb's law, and it has an electrostatic constant. And it's a big number. It's a big number. Something 10 to the 10th or something like that, 10 to the 11th. And this is a tiny, tiny, tiny number. So what happens is, if I may be so bold, you have the reality of these 2 masses in kilograms and the reality of their distance in meters. And that's the truth. That's what it should be. That gives it proportionality to the other fundamental forces. But there's not the right answer. It doesn't prove what really we see. We see the apple falling the speed it does. We don't see the apple falling the speed it would fall if it was just mass 1 times mass 2 divided by the distance squared. Because you have to factor in this tiny, tiny, tiny number, this gravitational constant. All right, so now we're going to make some progress. What if we have a thought experiment? Take the Earth again, but this time make it hollow. So hollow out the center of the Earth. It's got the same mass, but just compress the average density of the Earth such that you have a hollow space inside. And now you have, say, a thinner layer of sphere. And then inside that thinner layer of sphere, all the same size, right? We're adding density, so it's compressing it. So it's same mass. But now there's a hollow space inside. And let's just, for argument's sake, it's not hot and it's not going to kill you. There's no radiation, nothing like that. But let's put you, John, in the middle of this sphere. Dead center in the middle of this Earth's hollow sphere. Right at the very center where the Barycenter would be.
Okay.
What do you think it would feel like? Would you move? Would you be stuck? What would happen? What would it feel like to be in a spacesuit, protected so you're alive, but dead center in the middle of a hollow Earth, where the edge is compressed to the crust of the Earth, so it's far, far away, and it's a vacuum inside? What do you think it would be like?
Well, and you said you did say the center would be the Barycenter, so that made me think I'd probably just be like suspended there, like floating.
You would
I
be
think.
in an internal Lagrange point, basically.
Yes. So you're stuck. Not only are you not pulled to any direction, but you are unable to move into any direction. You would be fixed at the Barycenter itself. Okay. Now imagine, let's go back to Newton now. So Newton's force of gravity, mass 1 times mass 2 divided by distance squared times the gravitational constant. He had a thought experiment. He thought, what if there was a mountain, and on top of this mountain there's a cannon, and the cannon shot a cannonball? If there was no attractive force, the cannonball would just shoot straight forever and just go off the edge of the Earth. But it doesn't. It curves down to the Earth. Well, now imagine a higher mountain and a bigger cannon. Well, it would land farther away. It would make a longer arc, but it would still land on the Earth forever. Bigger cannons, higher mountains. Eventually, he proposed, you would get to a point where the cannonball would have an arc so far that it reaches to the edge of the Earth, and a little bit farther than that. And it would fall like it's falling towards the Earth, but it would fall to the edge as the Earth curves away. And then it would keep falling, but the Earth would keep curving away. So what he imagined was a cannonball that you could shoot far enough from a high enough distance that it would go into orbit. And it would orbit the Earth forever, like a satellite. And this was his idea. This is the force of gravity. So now let's replicate that. Let's say we have our equation, mass 1 times mass 2 over the distance of the center of gravity squared. And now, instead of you being in the center of the Earth, let's put like a little simulated Earth. Let's just call it 1,000 kilograms, whatever, arbitrary, right in the center. Put this object right in the center of the Earth on this Lagrange point. Now build a little mountain on this little simulated Earth and put a little cannon on top and start replicating the experiment. Tucker, what do you think would happen?
So you're still going to be fighting. I think once you have the object in the center, you're going to be fighting two gravities. Though the one from the object would be much smaller. So I think it would take much less energy to shoot a cannonball from that small Earth and get it to leave that Earth's orbit. So where it takes a vast amount of energy, like 17,000 miles an hour, to leave the surface of this Earth. I think that small one in the center, you're going to require much less velocity before that cannonball is pulled away from that Earth to the inner shell of the larger Earth.
Was the cannon on that object in the middle, or was the cannon still on the outside of the crust of the Earth?
It's in the inner one. So Tucker's got it right. So you have an inner simulation or version of the Earth. It's a real thing. It's 1,000 kilograms, whatever you want to call it. Make it tiny. So it's a spherical little object. As you shoot off the cannon, you would still have the same basic formula in play. You'd have the mass 1, the mass 2, and the distance from those two masses. But one thing would change. That would be the gravitational constant. So just like Tucker said, it would take less energy to create an orbital situation from inside this hollow Earth. But everything else would be proportionally the same. So you could do the same exact formula of the two masses and their distance, and that would create a force, but it's counteracted by another force, which is the force of attraction by this outer shell. And it would partially negate the force of what you would be currently calculating. It's exactly right.
Can we go back real quick? Because
let's do this.
You guys both, we both mentioned the Lagrange point, and I admit, today years old. I mean, it sounds a little familiar, but what is the Lagrange point, please?
So there's a spot between the Earth and the Sun at all times where basically the gravity kind of cancels each other out. It's the Barycenter. So if I stuck you there, you would just stay there in perfect orbit between the Sun and Earth at that diameter. You would basically become another planet shadowing Earth around the Sun.
Okay.
Equilibrium. You would achieve an equilibrium, so you're not tugged in either direction.
Gotcha. Okay, thank you.
And so if you put that at the center of something, you're not going to be able to move. You couldn't actively move your way out. Now I'm putting you in a zero environment, meaning you're in a vacuum, so you can't push against the air or whatever. So no matter how much you wanted to move, like you would be stuck in this one position, pulled equally in an equilibrium from all sides, all directions. No way to break out of this equilibrium position. And so the force doesn't go away. You would feel weightless. You would feel like you're floating. But the point is, you have, just like the sun and the Earth or any planet, you have all the force on you. All the force is acting. It did not disappear. It's just equalized in all directions, all the same amount. So same distance in any direction to the edge of the hollow Earth. Average density is the same of all parts of the hollow Earth. Therefore, you're pulled in all directions at once.
And you said pulled, but with the equilibrium piece there, it's not like you're being pulled apart. I mean,
because the gravity is so weak. That's the crazy part. You're being pulled in all directions, but the actual force of gravity is
it could be strong
weak
as well. It's just always equal. So now technically your body is not in a singular point, so you could be spaghettified or something like that. Or
that's what I was going to ask. Like, would it feel like you're being pulled? Would it feel like be uncomfortable, like painful, or would it just be like indistinguishable, undetectable?
I don't know the answer to that. I'm just because honestly, I'm making an arbitrary distance from the center point to the edge of the crust and how much mass is there, and I don't know the answer to that. What I'm trying to is a good question. What I'm trying to illustrate is when you have an equal gravitational attraction in all directions at the same time, at the same distance, they all cancel out.
Yeah,
so-
and you know what? I think I can answer that question. With a Lagrange point, no, you would not feel that spaghettification. You
I
wouldn't
think
feel
you're
like
right.
you're
Yeah.
pulled apart. You could even have a Lagrange point between you and a black hole and a star,
Yes.
things with incredible mass, but that Lagrange point is just where the two opposing gravitational attractions just cancel each other out. You wouldn't actually feel like you're being pulled apart.
Gotcha.
I think that's a perfect illustration. That's exactly right. And by the way, if you were to take, say, the sun and replace it with a black hole that's equal mass, you would not notice a gravitational distance difference. All the planets would still orbit exactly the same, meaning it doesn't really swapping out, because we're talking about center of mass.
Yep.
Like swapping these things out, it doesn't really change the force. Just like you're not pulled apart, like the gravity of the Earth itself doesn't crush you.
Yeah.
You know, like you're not crushed. I know you can't jump very high. You know, you can jump, but you're going to come back down again. But you're not. This illustrates, and I think going back to the space.com article, they start with a funny line, which is pick up a piece of paper off the ground.
Oh yeah.
Well, you just defeated the
Congratulations.
Earth.
Yeah.
Congratulations. You just overcame the Earth's gravity. So what I'm talking about and what we're envisioning is this proportionality. So imagine just without the gravitational constant, you would have mass 1 times mass 2 divided by the distance squared. And that would be extremely powerful force. Extremely powerful force. Adding in or multiplying in the gravitational constant cuts that force such that now it is the one of the four that is out of balance. The thought experiment is now saying, okay, what if we had a hollow Earth? So we have the same attraction of all the mass of the planet, but we're at the center, we're on the Barycenter, inside the Earth. The only thing formulaically that would change, if you set up a new simulated Earth inside, like not the full mass of the Earth, obviously, but just, it doesn't even matter, just miniature, it's just a miniature version. And you have a miniature sphere in there at this center point. You have a miniature little cannon, miniature cannonballs. You would be able to recreate an orbital pattern with the cannon at a certain level, but it would be less than the formulaic force of gravity. So imagine you don't know the Earth is out there. You don't know you're inside a hollow Earth. And all you have is John floating next to this little planet, doing an experiment, shooting a cannon off a little mountain. He would come up with what Newton came up with, other than one thing, which is the value for the gravitational constant would be different. It would be slightly less or more. It wouldn't be as small of a number. It would be a larger number, which would not reduce the force of gravity as much. But everything else would work.
I think I see where you're going. Yeah.
Let me throw another one in here because this is very interesting. This was not known experimentally for, I want to say like 200 years, something like that. There's a guy, I believe it was in the early 19th century, who is Cavendish, who created an experiment to experimentally determine what the value of the gravitational constant is. And he used a torsion device, a twisting device. He had mass, big mass, experimentally significant mass. I think it was lead, say 1,000 kilograms, whatever. And then on the end of a very, very, very long arm tied to the end of a string that had a known twisting torsion value, he had a little object ball at the end of that arm. And he would experimentally detect the force of the one object, the one mass, from the second object, the little test mass, and he knows the distance. So he knows what the force is from the amount of torsion, twisting. He knows the mass of one, mass of the other, and he knows their distance. And so when you know all those variables, you plug them into the formula, you can experimentally derive the gravitational constant, which he did. So now let me put you back in there, John. Now you have this little Cavendish experiment. Again, you're in the middle of the Earth. You have this test mass, 1,000 kilograms, whatever. You have this little Cavendish experimental apparatus, which has a string on it with a known force required to twist it. And you have a long arm, because this force is so weak, it's very difficult to experimentally detect the force at all. So you have a very long lever, essentially, at the end of the string, and a test mass at the end of that lever. If you were to run that Cavendish experiment again in the hollow Earth, what do you think you would find?
Something different. Ding, ding,
That's
ding.
true.
No, so I mean, the difference would be in the gravitational constant.
What do you think it would be? So we have three possibilities. The force of gravity is exactly the same, regardless if you're inside the hollow Earth or not. It's different in that it's weaker. It's different in that it's stronger. So there's three possibilities.
Is it weaker?
I think it would be. Tucker, would you agree?
I'm going to need you to ask the question again because I was playing with something in my head that we'll talk about here in a minute. So what were you asking?
So there was an experimental apparatus set up to test experimentally just the gravitational constant.
Mm-hmm.
And the way it was done was by having a string with a known twisting force. So you have to twist it so hard to make it twist. And at the end of that string was a stick or a rod attached. And at the end of the rod was a little test mass. And they put this next to a larger experimental mass, like a 1,000 kilogram ball of lead. And now they know mass 1, they know mass 2, they know the force, and they know the distance between them. And by testing now what that force is, by how much it turns, meaning how much the one mass pulls the second mass, you can solve for the gravitational constant. So this guy solved for the gravitational constant. And I'm saying if we recreate that experiment, that setup inside the hollow Earth, there are three variables or three possible variations that would be the outcome. One is everything's exactly the same as if you're on top of the Earth. Second is the force is greater. Third is the force is weaker. What do you think it would be?
So if you're at the actual center, I think it would be the same. Like if you could place that string directly in the center with the ball attached, I think it would be exactly the same. As soon as you increase your distance from that center, something's going to change. Because now you're going to have, you're no longer in a Lagrange point, really. You're going to be pulled more to the side of whichever side you're closer to.
And let's do this. Let's modify the thought experiment such that we don't have to take into account the exactitude, meaning let's just say it's not going to be, it's like where you can get rid of the mass of the human when you're trying to determine the Earth's gravity. So what I'm saying is, when we talked about the Newtonian experiment shooting a cannon, we agreed that it would take less force to put that little cannonball into orbit around the little Earth because there's mass on the outside that would be pulling in an opposite direction than the little test mass of the test Earth.
Yep.
So my proposition is that the formula would still work, meaning everything would balance. You would still have a mass 1 times mass 2 divided by distance squared relationship. But the one piece that wouldn't work would be the value of the gravitational constant. And I propose, due to having an Earth mass on the outside at some arbitrary distance from you, you would be counteracting, pulling in an opposite direction from the little test Earth with a little test mass inside. And so all you would be doing is adjusting the value of the gravitational constant and making it the value, meaning it wouldn't be as small, it would be a little bit larger. And you could still do all the math that we do with Newton's gravitational force formula. You would just have to adjust the gravitational constant a little bit because it would not twist as strongly. So the twisting force, this measurement of the force. So imagine, let's just simplify. I think we're getting too complicated, perhaps, on my part about making this.
No, I'm with you.
But let's just.
And I'm wondering if I'm actually seeing where you're going with this. So I want you to continue.
Well, let's simplify. I'm sure you've got it, but let's simplify. Let's just say there's two mass. Let's say instead of John being in the middle, there's John. Let's just say you're 100 kilograms, and then there's another 100 kilogram mass next to you, John. Okay. And let's say you're pretty close to each other, and you start, because you're in the center of this hollow Earth. You would obviously be attracted to one another. So the two.
There'd be a Barycenter between us, right?
Exactly. Yeah. Exactly.
Okay. Yeah.
You would have an attractive force. So you would slowly, whatever that means, you would start to proceed towards the Barycenter.
Mm-hmm.
Okay. And if you had Newton's formula, and you know your mass, and you know the other mass, and you know the distance between each other, and you can calculate the force by, let's not go into the definition of Newton's, but Newton's are defined. So the force of gravity is the units are in Newtons. And a Newton is a kilogram meter per second squared. Doesn't matter why, but we can go into that another time. But it's the amount of acceleration upon 1 kilogram. So 1 Newton is equal to the acceleration of a 1 kilogram mass by 1 meter per second squared. So let's just say you guys have, by the current formula, you know what your acceleration should be. You know how many newtons of force there are between you and the other 100 kilogram mass. What do you think if you did this experiment? Do you think it would be the same? Do you think it'd be higher force of attraction or lower force of attraction?
I still go lower, I think.
I would agree.
Yeah, because you're going to have some attraction between the two objects.
You're going to have attraction between the two objects in the center, but you also have the traction at all sides around you that are essentially pulling you outward in all directions at once, locking you in, meaning slowing your progress towards this new Barycenter between the two new test objects. So this counter position of the gravitational force of all the mass around you on the outside would delay or show a reduced force between the two at the center towards each other. That's my contention.
Mm.
So the little journey I was going on while you were doing that was, what if gravity is actually 85% stronger? And in our calculations, we're ignoring the fact that outside of all the physical mass we see, there's 85% more pulling away at the same time.
Damn, you beat me to it again.
Well, yeah. What do
I haven't proportioned it as such, but that is going to be obviously where we're going with this.
I was trying to screw around with it on my phone, but I'm gonna have to bust out like a real calculator and spend some time on that to see if I can make heads or tails of it. But I like the concept.
Yeah, I think I have not tried to balance it with because I think there is another issue, which is going to be, so let's just get rid of the pretext. So I'm proposing that the gravitational constant is not just a number to be used to get the force of gravity. It's a real thing. And the real thing is on the outside edge of a universe. Say we're in a bound vacuum, and the outside shell of our boundary has gravitation. It's got mass, it has gravitation.
And I could see that very well being where that 85% that we're missing is we can't see the edge.
Well,
and the edge is where it's all at.
I agree. But here's the thing, the edge, and not to go too far down the rabbit hole, but the edge is not fixed. It is also expanding.
Yep.
So as it expands and it moves, our place relative to the edge changes as well. And just to put a kind of a visual on this thing, I don't see it as a singularity that's growing spherically. I see it as a torus shape or a donut shape that's expanding out. And imagine, so call back, there's a balance in the wave in the wave properties, equal and opposite. So we did a hypothetical, if you had a guitar string and you plucked it, is the vibration going to go up one side of the string or both sides of this, right? We discussed it. So it goes both sides. So imagine, instead of a singular from nothing something explosion, big bang, imagine two things hit each other and they begin this vibration. They begin this pluck of the string. But the pluck of the string is in equal and opposite directions. So you would have our universe, meaning the clockwise universe, and you would have a counterclockwise universe. You have positive length and you have negative length, but imagine them growing inside a torus. So the donut shape is expanding and progressing on one side, going one direction, is positive length or our universe, and going the other direction around the donut is the antimatter side or the negative universe. So you would have two in balance. And then they're both growing as the shape of the torus grows. And the true nature of the force of gravity is mass 1 times mass 2 over distance squared. But what we're stuck with is being like inside the cake of the donut. And so there's a counteracting shell of the edge of the donut that's pulling against our inner force. So it's really three bodies from the get. So you have two bodies. Now I'm jumping ahead. You have two bodies that are mutually attractive, mass 1 and mass 2. But what we call the gravitational constant is the third body. It's just in a shape and at a distance and a mass so ridiculous that it's like we're inside the jar. Literally, we're literally inside a jar. Not just a metaphor. My proposition is it's literal. We are inside a jar. We can test experimentally our force of attraction between two masses. We know their distance. We can measure the force. And what comes out is not equivalent to mass 1 times mass 2 over distance squared. It's so much tinier. So what do? We make up a new term, a gravitational constant term that counteracts or minimizes or reduces when you multiply it into the value, such that it makes it so out of balance with the other three fundamental forces.
Wow.
I like it.
Can I ask about the expanding donut? This might not be relevant, but because
do it.
The donut has the hole in the middle. As the donut is expanding, I mean, the hole is expanding too. Or is it possible the hole is shrinking, like the cake of the donut?
By the way, this is next episode. This is literally the bulk of what we're going to talk about.
Great. That's
because Einstein. Here, let's jump ahead real quick with a teaser. Yeah. Einstein changes everything by saying gravity is not a force. Gravity is the curvature of space-time. Now, mass influences the curvature of space-time. So Newton's formula is technically correct in that it works as long as you're within the same frame of reference. But it doesn't always work because not everything's in the same frame of reference. And we'll go into that later on. But the point is, yes, there is a curvature, and the curvature is fundamentally important. meaning the curvature in the torus itself, the donut itself, it has special properties that influence the outcome. But if you don't know it's there, it's very mysterious. But yes, the inside of the donut is different from, I'll jump ahead here. There's positive, negative, and flat curvature. Experimentally, we have determined we are in a flat natured universe. The curvature, the sum of the angles of a triangle are 180 degrees. And we're in this flat, infinite plane. But what I'm saying is that's analogous to standing on the Earth, thinking the Earth is flat because you can't see the curve.
Yeah.
So if we imagine, and this is not mine, obviously, this is many other scientists have proposed this, the universe doesn't necessarily have to be flat, even though experimentally we can only see it as flat where we are. So in a big enough universe, you might have curvature that's undetectable at our scale. But if the curvature is not spherical, because a spherical is positive curvature, but what if it's not positive? Well, what if it's negative curvature? So you have a sphere, which is positive, and then you would have like a poncho or a piece of lettuce that would be considered negative curvature, where it's flippy floppy. So it doesn't curve on itself, and it's not flat as a plane. It's got folds and it's like a saddle shape is technically what's called saddle shape. So you have like a sphere, a saddle, or flat. But a torus has all three. So on the inside of the donut hole, great get here, John, by the way. I love that you went there. That's negative curvature. It's curved like a saddle. On the outside of the donut, it's positive curvature. It curves around like a sphere. And then there's like this little border point as the two transition that's functionally flat. And so this will work in, a spoiler, to the solution to the three-body problem, which is as you add in a third mass, they no longer are symmetrically revolving around a barycenter. There's a break of symmetry such that some of the mass, one of the masses, of the three, unless you have, by the way, there are solutions to the three-body problem that do put them in periodic orbits, but they're very, very, very specialized orbits that are, not natural. But you can make it such that you can have a periodic orbit with three massive bodies, but they have to be in a certain position of equilibrium in their trajectories. So what I'm saying is, if you have an imbalance amongst those three items, because there's a fourth item out there, there's a fourth variable, the gravitational constant itself, which does not act 100% equally in all directions when you add three. Now, two objects rotating around a given barycenter, they do balance out. So the force of gravity holds true. I mean, it's predictable. But when you add that third object, it's really now going to four objects. Because if you count the outer shell as one of the masses, one of those three bodies, if they're not exactly positioned in a very specific way, that they're fundamentally symmetrical, you're going to have an imbalance. Very tiny, but it's going to be an imbalance, and it creates a chaotic state. Makes it unpredictable.
Basically, in their system, there is no barycenter the way we think about it. That barycenter would actually move almost as a fourth object in space-time until one of them came back, and it was so chaotic that it flung it out or, crashed them into each other.
But what I'm saying is, what looks like chaos is only chaotic if you don't know there's an outer shell. Once you apply the outer shell, now finding the distance and the mass of this outer shell, that's going to be the trick. So trying to determine, as these things move, where they are in relation to the outer shell is going to be the tough part. But I would propose that you could simulate, a vast number of options of what the mass is, mass energy, by the way, we'll get into that later, but mass or mass energy of the outer shell versus distance. So each object will not be the same distance on average from the actual edge, and the shape of each edge inside the donut hole versus outside the donut hole, they will not be equivalent. When you have three objects, there is an imbalance, but it doesn't mean it's unpredictable. It just means we can't do it because we're not factoring in one of the variables. So if you factor in the gravitational constant is not just a singular number, but it is a mass at a certain distance for each of the three bodies, you should be able to correct for that.
Lovely. And the timing is great here. We're like just about at 90 minutes. So some nice teasers. For just like final thoughts, I'd like to just throw a question for pondering. I don't know if this will even come up, but just something to, I'm curious, like what, if anything, is at the center of the donut, and could it be related to the everything bagel in the movie Everything Everywhere All at Once? Half joking, half, but like, yeah, that's a really interesting idea. And but yeah, any
Well, it takes
other
away the concept of a center, and this is one of the ideas that we have in modern astronomy: is any way you look, any direction, it's all the same. So when you're inside a torus shape, there is no center. Not when you're inside. Now, from the outside, this goes back to dimensionality. Looking down upon a donut, you can see there's a donut hole on the inside, outer shape. But if you're inside the cake of the donut, every direction to you
is more cake.
Is more cake. You don't get to see. So that deviates. Great question, by the way. That deviates from the Big Bang hypothesis, where there is a center that started, and then everything is expanding from that center. And as it expands, it increases the rate of expansion. It's dark energy. So to the point, I think that's exactly the right question: is why do we have a center? Like, what is a Big Bang? Is a singularity, an expansion of a quantum state where you have infinite density, infinite mass, infinite energy, but it's a singularity. It's a single point. Points where? Nobody knows. Nobody cares. But from that point, it expands in all directions, and it's creating space as it expands. And what I'm saying is, if it starts as a collision between two objects, and these two objects, say they have wave properties, and they're slamming into each other, is a constructive formulation of two opposing waves, such that it creates more dimensionality, and it creates a donut-shaped explosion, which is also not just expanding, but it's spinning and it's twisting. So imagine the donut is getting bigger, so the inside hole is growing, the outside diameter is growing, and it's rotating. The cake itself is spinning. So you can have multiple dimensions of expansion simultaneous, but none of them look like the center because there is no true center. The center is a hole. The center is
outside.
It's outside, exactly. The center is truly there, but you have to be up a dimension to see it.
Yeah.
So call back to flatland.
Right.
If you're a circle and I'm a circle, I look at you, you look like a line to me, and I look like a line to you. But if I go to above the paper, I can now look inside you.
Yeah.
I can look inside your circle. And theoretically, if a sphere looks like a circle to another sphere, etc., you can keep on. It's a fractal relationship, is my point.
Nice. Well, yeah.
Covered a lot of ground there.
Yeah, totally. Yeah,
Did a good job.
This is great. I'd say we wrap up here. I will say we'll be off again next week. So hopefully anybody listening, hopefully you've been enjoying the Colin archive episodes. I think we've got a couple more to put out there in cases like this. where we're going to be off. But the following week, we'll pick this back up with Einstein's gravity, like Bob mentioned. So um, we'll get that side of it, and then I think in the episode after that is where we'll finally get to the solution concepts here. So that which I think we've already hinted at, right, a little bit, but I don't want to go too far in that.
You're right. There's some special sauce though. I'm going to save the special sauce for the end. We did hint at it. I think everybody who's can see what's coming, but there is a special thought experiment to get us there at the end that cannot be missed.
Yeah, I'm very looking forward to that. I can't wait. So awesome. Yeah. Well, until then, thank you guys. If you're listening, please consider leaving us a review. You can contact us at sendingpoets@gmail.com. But until then, in the words of John Adams, you will never be alone with a poet in your pocket.